1.3 Tree diagrams. A tree diagram is a tool used in mathematics, probability, and statistics to calculate possible outcomes of an event or problem and to cite potential outcomes in an organized way. Okay, so there's going to be each stage in the event is illustrated with a new set of branches. So for example, the first toss of a coin is going to be all of these outcomes. Okay, and then our branches go heads and tails. And then the second toss of a coin, because we would, if we rolled or tossed the first as heads, then it's heads and tails. If we toss the first as a tail, we still have the options of heads and tails. So extending from each, the end of each branch in the previous stage. To identify a given outcome, what we do is we read across the distinct path. So we would read this as heads and then heads, and that would be our outcome, head, head. Or we can read heads and tails, and then this would be our outcome, head, tails. So to determine the number of outcomes, what we do is we count the number of distinct paths across the tree. Okay, in other words, we could count like 1, 2, 3, 4. There are 4 outcomes when tossing a coin 2 times. Okay, investigation 1. Suppose you need to put together an outfit for a funky outfit day. You have 3 shirts to choose from. So you have white, blue, and green, and 2 pants to choose from. You have jeans and then dress pants. We're going to use set notation to list the number of different outfits consisting of a shirt and a pant using the forms provided. So what we can do is the set notation would be the squiggly brackets, and we're going to go white shirt and jeans. Okay, or white shirt and dress pants. Okay, we can wear a blue shirt and jeans, or a blue shirt and dress pants. And we can wear a green shirt and jeans, or a green shirt and dress pants. Okay, so in this one, we have a total of 6 different outcomes. Okay, we have 6 different outfits that we can choose from. Now, as our sets get bigger and bigger, so maybe as we have more and more shirts and more pants to choose from, it becomes very tedious to use set notation to list all of the outcomes. Another way of organizing our outcomes is to actually do this in a tree diagram. So from the investigation above, we're going to display all outcomes in a tree diagram. So the first stage here is going to be the shirt. Okay, and how many ways can we choose a shirt? We can choose white, blue, or green. And then the second stage is where we can choose pants. Okay, so if we choose a white shirt, we can choose jeans or dress pants. Blue shirt, we can still choose jeans or dress pants. And a green shirt, we can still choose jeans or dress pants. Okay, and if we count these, 1, 2, 3, 4, 5, 6, we can say the total number of outcomes is 6. And if you take a look, these 2 match. Now, let's do a little bit of an extension on that. Suppose that you do not like to wear a blue shirt and jeans together. Okay, so that's blue shirt and jeans. So you don't like this one. Okay, you also don't like a green shirt and dress pants together. So green shirt and dress pants. You don't like this one either. So what we can do is we can pull probabilities from this tree diagram. So what's the probability that you choose an outfit that you like? So probability that you like your outfit. Okay, well, we have 6 outfits, and you like 1, 2, 3, 4 of them. Okay, which is 2/3. And now the probability that you don't like your outfit, okay, we can write that as like complement. We can either count them directly as 1, 2, so 2 out of 6, or we can do the indirect method. So 1 minus the 4 out of 6 is going to give us 2 out of 6, okay, which is 1/3. Okay, So let's extend our tree diagrams, and we're going to call this a probability tree diagram. So this is illustrating the exact same tree diagram. However, this time what we're doing is we are assigning probabilities to each outcome. So the heads and tails is going to be 50-50. But then once you roll or toss this heads and tails is again 50-50. These are independent. They don't rely on one another. Okay, so we continuously label these 50-50, okay? And then this heads and this tails, 50-50. And if you think about it, these add to 100%. These add to 100%. These add to 100%. So we're still taking into account all of the different outcomes here. Okay? So here's a connection that we're going to make in the next few lessons. Okay? So the total here, there are 4 outcomes. So that means each one of these outcomes has a 25% chance, or 1/4, 1 out of 4, chance of happening, okay? Probability of happening. If we actually take a look and we move down the branch, like across the branches, 0.5 times 0.5 gives us that 0.25. And then 0.5 times this 0.5 gives us that 0.25. Okay, so let's just keep that in mind so that when we see it, we're understanding it. So this time what we're going to do is we're going to construct a probability tree diagram. Okay, so assume that it is equally likely, okay, so that's 50-50, that a baseball player catches a ball or misses a ball. And we're going to construct a probability tree diagram to display all possible outcomes and their probabilities, okay, when attempting to catch a ball twice. Okay, so we're going to say catch, and we can call this miss. And then we can say, as soon as you catch it, we can still either catch it or miss it. And if you miss the first one, we can still either catch or miss the second one. So this is the first throw, and this is the second throw. What changes this from a tree diagram to a probability tree diagram is now we're going to say what the probabilities of each of these outcomes are, which is 50-50 for every single one. And if we multiply 0.5 times 0.5, this outcome, which is catch, is going to have a 0.25 probability of happening. And a catch-miss, 0.25. And a miscatch, 0.25. And a miss-miss, 0.25. If you think about adding all of those up, they all add to 1. And now let's work with our probability tree diagram to find the probability of catching 2 balls. So that is going to be a catch situation, and that is this one right here, 0.25. Now, catching at least 1 ball. So there are 2 situations here. We either catch it or miss it, or it's actually 3 situations. We miss it, then catch it, or we catch it, then catch it. All of these have a 0.25 probability of occurring. The only situation that we don't have here is missing the ball twice. So that's 75% probability, or 0.75. Now D, what's the probability of catching 1 ball and missing 1 ball? So this is the 2 outcomes, a catch and a miss, or a miss and a catch. That's what that's going to look like. So this is going to be 0.25 plus 0.25, so that's going to be our 50%. Okay, so we're going to reinforce this a little bit. So assume that there is a game where you spin a spinner labeled 1 to 3 and toss a coin. So this is going to be spinner. And then you toss a coin, which is heads, tails. So let's go ahead and construct a probability tree diagram to show the possible outcomes. So the possible outcomes are going to be 1, 2, and 3. I'm going to go ahead and label the probabilities right now. So each of these, because they're equal sections on the spinner, are going to have a third probability that we're going to land on them. And then once we get, if we spin a 1, we can either get a heads or a tails. If we spin a 2, we can get a heads or a tails. And if we spin a 3, we can get a heads or a tails. At this point, these are half or 50%, half and half. So if we're thinking of a third times a half, each of these has a 1/6 probability of occurring, which makes sense because there are 6 outcomes, right? So if you think about the total, you're thinking 6. So because there are 6 outcomes, each one has a 1/6 probability of happening. Now, B, what is the probability of spinning a 1 and tossing a heads? Well, that only occurs one way, spinning a 1 and tossing heads. So that's 1/6. We can just read that number there. And what about C? Spinning an odd number and tossing a tails. Okay, so how many ways can we do that? So 1 is odd and tails. Okay, so that's 1/6. And then 3 is odd and then tails. So that's 1/6. So I get 2/6, which is 1/3. Okay, and the last one. Determine the expected number of times you would spin a 2 and toss a heads if you played this game 25 times. So the expected number of times of spinning a 2 and tossing a heads is going to be, okay, so we're playing it 25 times, and the probability of a 2 and a heads is 1/6. So we can go ahead, get out our calculators, and just do the 25 divided by 6, which I get 4.17. We'll round. Okay, last topic, the complement. So a complement of event A is denoted as either like A, I call this prime, or this squiggle, like approximately A. Okay, but it's pronounced A complement. Okay, it's a set of all possible outcomes that is not included in the event. Okay, so this is when event A does not happen. So if we actually take a look at these Venn diagrams, okay, event A is here. It's the red. And if we think about the entire box being the universal set, everything not in A, which is zigzagged, is going to be A complement. And as an equation, we have both counting and probability. Remember the two themes right now? So the number in A plus the number in A complement is going to give the number in the universal set. Okay, for probability, the probability of A and the probability of A complement is going to equal 100%. Okay, these two equations right here are just those first equations that are rearranged. So if you think about isolating for A, the number in A complement, we're going to bring over this number in A, and instead of being positive, it's going to become negative. So these are the same equations, they're just rearranged. So, example 4. What is the probability that a randomly drawn integer between 1 and 30 is a perfect square? So, let's talk about perfect squares. Okay, that set is 1, 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. Those are all of the perfect squares. And now the total number between 1 and 30 is 30. Okay, there are 30 integers there. So, for A, probability of a perfect square is 1, 2, 3, 4, 5. 5 out of 30. Okay, so a sixth. And the probability of not a perfect square. So I'm going to go perfect square complement. Okay, we can do this one of two ways. We can either count all 25 numbers that are not a perfect square. but that's a little tedious. Okay, so instead what we're going to do is we're going to go 1 minus a perfect square. Probability of a perfect square. So 1 minus a sixth, we're going to get 5 over 6. And if we actually want to show that these probabilities add to 1, we can just go a plus a complement equals 1, which we can see a sixth plus a fifth, 5/6 equals 1. 6 over 6 equals 1.